Okay. Thank you very much, folks, for joining us on our final honors program colloquium of the fall 2021 semester. We're very excited to be able to continue our, 4 or 5 years running now of having Dr. Ben Newman give us a talk on viruses at the end of the fall. Prior to this was a little bit more of a purely academic discussion, but now in the world of COVID, it's become our everyday life. So Dr. Ben Newman, who was the chair of the biology department here at A&M Texarkana and is now the chief virologist at the Texas A&M University Global Health Research Complex down in College Station, is going to be talking to us today about basically SARS CoV-2 and its variants and vaccines. Very timely. After his talk, we should have some time for questions. And yeah, take it away, Dr. Newman.
All right. Flip through the slides, get the right one. Share that screen. Move the thingy up, and we are rolling. Yeah, all right. Hello. I saw a bunch of people saying hi in the chat, and that was very nice. Nice to see you and hear from you anyway. So yeah, okay, where are we now? I figure you're probably going to want to know about Omicron, so I put that up front. I thought you might want to know about like vaccines in kids. That's the latest thing, so I got a chunk of that in the middle. There's a little general vaccine stuff that we can split over. Oh, I stuck ivermectin in at the end just because it doesn't go away, so I'm going to keep talking about it too. Here we go. So, state of the world, 2021, November. Looks about like this. So this is our standard graph. We got time going along the bottom, and we've got basically market share of each different variant over time. So you see in March, we're at, I don't know, maybe 70% alpha, which is the red block. And just the tiniest little sliver of delta, bless, yeah. Fast forward to now, that big blue chunk, that is delta. But if we go over here, so I'm gonna move my little picture over, there we go. This breaks down the deltas. There are actually 160 sub-delta variants that are being tracked at the moment. The 160 number was from last week. I haven't checked this week for the update. It's probably more. But I think the important thing here is that for the most part, these don't seem to be gaining market share on other Delta branches. So we look at this kind of like a race, and whereas Alpha was faster, fitter, and better, there we go, than all the variants that came before, and Delta did the same thing to Alpha. It looks like all these things are roughly on a par. So one Delta is roughly the same as another Delta as far as we can tell right now. But of course, you're here to talk about Omicron, right? Yeah. So where do we get new variants? Well, yeah, 2 mechanisms. The first one is that the virus changes over time, and you know this by now, but actually the virus changes at a very reliable rate, almost like a little clock. So here you can see from the first couple of months of the outbreak, that little diagonal line is running through. So when we go up a mutation, or when we increase mutations, we go up one little level each time. And then the lines show how these are connected to each other, like which ones come from which branch. And so, yeah, it's like a reliable little timekeeping device that changes all the time. And we also dodged 2 big bullets so far in 2021. So the first was the pig coronavirus that jumped over to children and made them very sick in Haiti. And this is not something anybody particularly expected, but it happened, yeah. And thankfully that was caught in time. It got to a cluster of kids, but it did not spread beyond that. But this pig coronavirus is pretty common, and it looks like it did not need many changes to jump from pigs to people. So yeah, it'll happen again at some point, and I hope we are watching as well. The other bullet we dodged was the They call it a canine coronavirus, but some parts of it look more like the feline, the cat coronavirus. It's somewhere in between, I guess. Yeah, that made somebody so sick they ended up in the hospital, but opposite side of the world, Malaysia. Thankfully, neither of those amounted to much more than you're reading about here. But there are a lot of viruses out there and they move from species to species all the time. It's just what viruses do. And so eventually, yeah, eventually all good things end, and one of these is going to get us. And so the question is going to be, are we ready? And can we stop it before it gets too big like this one did? Omicron, that's what you want. So Omicron right now is showing up as almost 13% of the sequences from the continent of Africa. But compare the number of sequences turned in last week from the continent of Africa, 607, to the number from Europe, most of which is coming from the UK, which is 54,000. So Europe is pasting all of Africa by 2 orders of magnitude, or you can look at it the other way. Africa is desperately underserved in terms of genome sequencing. The reason this is so high is that there's a test, like a standard screening test you can do, that'll actually tell you pretty confidently whether or not you've got an Omicron. And so they're sequencing all the ones that come up as potentially Omicron, which is why you have this high number right now. I think overall, though, they're believed to be less than 1% of the cases, even in Southern Africa right now. So it's not a virus that is doing particularly well. It's just a virus that is a little bit weird and that we need to watch. So what is Omicron? I mean, everybody wants to know, like it's a new superhero. What are its powers going to be? Can it shoot lightning out of a ring or something? Yeah, what's this going to do? We can get some picture of this based on shared mutations. So if it has the same mutation in Omicron, which is here in the middle, as we found in Alpha, we can say that, okay, maybe it's going to be a bit like, this one worked in Alpha. So in the blue region, we've got mutations that are likely to be evolved in kind of low-key immune evasion. It'll escape past a couple of antibodies, but it's not going to move the dial very much. And so you can see we've got several, 6 shared mutations and 3 unique mutations there. Then the yellow area is the one of real concern. So this is the binding surface between the virus and the cell. And this is the surface, this is like the bullseye, where we really want our antibodies to land, where we want our immune response to be laser focused. That entire surface is changed. 10 out of the, 30 or so amino acids there are different in the Omicron variant. So it's like trying to shoot at a target that has no bullseye. You can score some pretty good shots, but you're not going to get a 10. Yeah. So I would expect some degree of immune resistance based on this, but it's hard to know exactly how much. And on the other side, the glass is half full of orange juice today, side, the spike overall is still 97% identical to the original very first spike that we ever found. So most of the immunity, particularly the white blood cell immunity, should still work just as well that you would get from a vaccine, for example. So it's not all bad. It's just kind of all a little bit too different to confidently predict what this is going to do until the tests are done. So you want to see how they do those tests? They're kind of neat. This is a thing called Biocor, they used to call it. That was the company that sold it. So it's a 2-step test. The first one, you make a nice flat surface and you cover it in receptors. So you cover it in the part from the human body that the virus wants to bind. Then you make up a big old batch of spikes with different mutations. And one at a time, you're going to let these spikes just sort of tumble across the face of all those receptors. And if a spike sticks, then you get a signal and our line will start to go up. So they show it always for 5 different concentrations. And let's just look at the top one. So you can see that as you're washing more of this virus over, it binds pretty quickly and then it kind of levels off. It's sort of saturated all the binding spots it can find. And so if we have a virus that binds better, we expect these lines to be higher. So like the top two are shown at the same scale. So that's 0.4 on both of them. And look at the top concentration here is at about 0.45. And the top concentration here is about 0.6. So that's one mutation you find in Omicron and also in Alpha. And so that makes much better binding, like considerably better, almost, not quite 50% better, but maybe a third better. Other half of the test is you sort of switch off the spigot that is bringing your spikes in, and instead you just wash over nice saline, just like eye drops. And so as this washes over, some of the spikes are then going to come loose. And so you can measure how well the spikes hold on after they grab on. And so the normal rate is that they drop off about this quickly, just like that. And then look at the ones with this 501 mutation that you find in Alpha and Omicron, and look at that. Those just hang on. It is a sticky spike, better at grabbing, better at holding on. In contrast, some of the other mutations you find in Omicron are like this one. So this one tops out, instead of at 0.45, it tops out at about 0.3. So that's not good. That's much worse at binding. And look at the fall down curve. It just drops straight off a cliff compared to this. So you can say that Omicron has a mutation that makes it better, and it has a mutation that makes it worse. And it also has this mutation, which makes it just about the same. So put all those three things in there, and I think you get unpredictability. So that's what people are saying. We know what some of the parts that are in Omicron do, but we don't know what they do together. Yeah. And so that's what we're trying to figure out. But the other things that we know, so there's another path to success, which is not even involving the spike. The virus can change a different protein that's kind of on the inside of the virus. It's called the nucleoprotein, or we abbreviate that as N. So like in the Delta variant, so this is an assay where you're trying to build as many virus particles as you can, like as fast as possible. I mean, I imagine this is a game show, just, popping those little viruses together, one after another. With the normal version of N, you can make this many viruses. So it's going to be one, because they normalized it to that. With the version of N that you get in the Delta variant and the Kappa variant, you get about 10 times as much assembled in the same amount of time. So it's just super efficient. Now, Omicron has got this one. It's about 3 times as efficient, maybe 4 times as efficient. So it's okay, but it's not Delta. Yeah. And what we've seen so far is that Delta is a beast, and it pushes out and actually drives to extinction all these other viruses. All the viruses that have the mutations that I showed you a page or two ago, those are all extinct now, and they were driven there by Delta. So yeah, it is a big and open question whether Omicron can actually compete in Delta's world, because it is very much Delta's world now. And I don't know, until something changes. Okay, enough about Omicron. Let's talk kids. Yeah, kids and vaccines. So you've probably heard people say, maybe even on the news, but probably not me, I don't think kids can even get COVID. Who says they get it, and why should we even vaccinate them? Here's the data. So this is from the FDA meeting in October. And so this is going in and looking in their blood for antibodies. Now, they're not antibodies against the spike, because you can get those from the vaccine or from an infection. They're antibodies against that N protein that we were just talking about, which is not part of any of the vaccines that you would take. And so if you have antibodies against that, that means you had COVID at some point, whether or not you knew it. It's a very good marker of COVID prevalence. And so you can see in older people, it tops out. About 15% of older people have markers that show that they had COVID at some point. Pretty bad. But then look at the yellow line. Those are the 5 to 11-year-olds. They are the single hardest hit group in terms of being infected with COVID-19. Seroprevalence in this particular study is around 36%. There was another study that came out around the same time that actually found 42% in a different American population. So somewhere between a third and half of kids this age have already dealt with it once. And if you think they can get it and they can't spread it, that's also a thing that is not correct. That is not good science. Yeah. So there you go. All right, next slide. But people say, well, COVID doesn't kill the kids. So, screw them. Yeah, which is not our policy or a very nice policy, frankly. But it turns out that little kids are actually pretty hard to kill. Yeah, which is good. It's my son's 18th birthday today. We made it. Yeah. All the way to adulthood. And yeah, congratulations to him. Even so, 2% of all the deaths among kids age 5 through 11 over the past year were from COVID. 2% of all their deaths. That's a lot. But the thing that really gets me is look over here. So this is the number of kids of each age that have died of COVID in the US only. And look at the ones who are under a year old, 130 little tiny babies. So the idea, I think, behind vaccinating the kids is that, yeah, you're going to protect them, and they're pretty hardy little things anyway, but much more so, you're protecting their younger brothers and sisters, and you're protecting the older members of the family, because see, those numbers start to rise up, and then, yeah, they continue to rise with age, you can be sure. So that's the idea kind of behind all of that. And the other idea is that in contrast to those deaths, 95 deaths over that period, you also had 5,200 cases of this multi-system inflammatory syndrome. This is the kids' COVID that's really bad. 60 to 70% of people have to be admitted to intensive care. The rest are just admitted to the hospital. 1 to 2% of those kids die. This is found only in younger kids, highest in kids who are age 6 through 11. So this is pretty serious and doesn't happen every time, but happens enough that, boy, I wouldn't want it to be my kid. So anyway, this is some of the data behind that decision. Now, if you're interested, well, how's influenza doing this year or, in general? The red, green, and blue lines at the top show you influenza cases, and this is the buildup. So as each new case comes in, it just gets up there, and then when flu season's over, it levels off. So these are pediatric hospital admissions related to the flu in past years. And we sort of topped out between 20 and 30 per 100,000 population. Flu has always been known as a virus that preys on the very young and the very old. And so this was considered really bad and is really bad. COVID's the yellow line. And so you can see it doesn't really have a season. It just sort of beats people up all year long, but it gets up to just the same rate as the flu used to. So COVID is causing as many hospitalizations as a virus that was considered a specialist kiddie killer in the past. So yeah. And how's flu doing these days? Basically dead. Yeah, basically on life support. 9 total pediatric influenza hospitalizations were reported in the 2021 flu season in America. 9 total. I believe there was 1 fatality last year, but not this year. So yeah, going from tens to hundreds of fatalities a year to less than 1 per year just shows that under the current conditions, with some people wearing masks and some people social distancing and people just watching, paying attention, every virus that we know of is on the decline. They're basically all on life support, except COVID. COVID is that much better at spreading than all of these other viruses. You can show the same curve for chickenpox. You can show it for measles. All these things are way down compared to historical norms, but COVID just keeps on trucking. So there we go. All right. If you know somebody who's vaccine hesitant, one of the things they might have cited is that I'm worried about having myocarditis, or maybe the kid getting myocarditis. Not all myocarditis are the same. Yeah, as it turns out, this I did not know. This is from a different presentation to the FDA. So you actually get spontaneous myocarditis a fair amount of the time. So 16% of these patients are, and if you look, disproportionately male. So these are 15 to 20-year-olds, And look at that. Yeah, it looks like about 10 males per female, maybe 8 males per female. Yeah. And then this incidence drops off. So this is spontaneous myocarditis from any cause. With normal myocarditis, this is the way it progresses. So the scale bar here on the side is showing people who got back to full heart function. And you can see that a couple of them get back after, 3 days. And then by about 15 days, you've got maybe 3/4 of them have got back to full cardiac health. The other quarter never do. It's permanent heart damage and lasts forever. With normal myocarditis, when kids get that inflammatory syndrome, the special kitty COVID version, it also causes myocarditis. It causes it about 16 times as often as vaccination does. And you see it's a little different. They get over it more completely. About 95% will get over it. And they'll get over it in less than 10 days in almost every case. Compare that to vaccine-induced myocarditis, and it's super short. Everybody has basically made a full recovery after 4 days. And we also know that the vaccine-associated myocarditis always comes with a very high fever. So we don't yet know if medicating that fever, just taking Tylenol or something, is enough to prevent the myocarditis. It might be, but we'll have to wait for the study to come in. But yeah, even in that case, it's very short. Full recovery is seen in just about everybody. And the overall rate of this is about 1 per million people, whereas the rates are much higher if you actually get COVID, that you will get myocarditis regardless of your age. So there you go. Okay, we don't really need this one for anything except to say that kids are now a much larger portion of the people who are catching COVID and also getting hospitalized for COVID. They're up to 10.5%, whereas they started out way below 1% a year ago. All right, so this is what are we going to do about this section of the talk? There are actually a lot of potential targets in SARS-CoV-2 that we could just be beating up. We could be ganging up on this virus, and it's going to take time. People have gone after the obvious targets, the ones with easy assays that are kind of quick and simple to do first, but eventually we'll get to some of the better targets, I think. So if you're looking at what are its weak spots, what are the soft spots in SARS? So all these that I just colored in yellow, these are parts of the genome. So this is the beginning, this is the end of the SARS genome, and each block is a different gene of the virus. These are things that are there to shut down parts of your immune system. And they are pretty effective. There are actually a couple down in this area as well that I didn't mark. These are things that make like a little sewer pipe that the viral components can travel through. The virus will make a sort of secret factory for itself, and this is the conduit between that and the cytoplasm. The virus has to go through this entire process called RNA capping. It has to put a special little group on the top of its very own genome, and it brings all the tools to do this. The virus is completely dead if you take away any one of these tools or any of these immunosuppression aids or any of the proteins in the pore. Scientists have shown this. Same thing, RNA making enzymes. We've gone after this half of this one with a couple of drugs and nothing on the rest. There are a couple of things that work like keys that make these work. Nobody's working on them yet in particular. There are a couple of enzymes that chop the virus into the pieces that will actually then work. And we've got a little bit of action on this one, but none on the big one yet. So yeah, there's still really a lot of ground that we can cover. There are a lot more ways on the table that we can beat up this virus. And I am all for that. Yeah, join me and be a COVID bully. Yeah, just beat this thing into the ground. Yeah. So here's our scorecard right now. We got 2 drugs against the red enzymes, 1 against the purple, and not a blessed thing against all the rest of it. So yeah, there's stuff to be done for sure. And our vaccines are all entirely targeted to the spike, whereas there are other things that they could also be targeted to that might help a little bit more. So there's room for improvement there as well. If you're interested, this is the new Pfizer protease inhibitor drug. And it works okay, but you have to look at the clinical trial. So they tested this on people the day they were PCR positive. And I think they were just scanning them to see anybody that came up PCR positive, like if somebody in your house was positive. So they caught them real early and they gave them this before they were sick. And when they did that, a number of them did not go to the hospital who we would expect to have gone to the hospital otherwise. So that's the full function. And it's very nice. They did a very good job in constructing that study. But this does not mean, and almost certainly does not mean, that this would actually protect a person who is in the hospital already. So what everybody wants is a drug that'll pull you back from death's door and say, not today, COVID. And that does not exist. We have preventatives that you can take basically the way people have taken ivermectin in the past. Only this one works. Yeah, so there we go. This is the other drug. This is the Merck drug, and it's called molnupiravir. And it doesn't actually hurt the virus directly. What it does is it puts a thing that looks kind of like a nucleotide, but is a little bit tweaked into the virus. And once that is there, the virus will then try to put in a base that matches it. So if you put in a molnupiravir, it looks a lot like the C nucleotide. It will get incorporated in the genome. And then every time the virus tries to copy that genome, it knows that A binds to T and C binds to G, just like your high school biology textbook knew. Only it's A binding to U because it's RNA, but whatever. Let the A plus kids worry about that. But the thing is, when you got a molnupiravir in your genome, what binds to that? And the answer is everything binds just about as well. So it's just a site where you force the virus to change something that it did not want to change. And the more of these you can sneak in there, they're like little Trojan horses that just keep beating up the virus and basically paying it forward. So kind of neat, yeah. But again, will work when given on the day you first test positive. And there is no indication that this thing works after you're already sick or in the hospital. They're doing those trials, but I am not optimistic because nothing else like this has worked in that way. Okay, RNA vaccines, not new and actually quite old. The first one, clinical trials on the first one published in 2008, actually started in 2007, which is the year the first iPhone came out. So yeah. You have an iPhone 1 in your pocket? Yeah, I have an iPhone 7 and people look at me like I'm a weird throwback from caveman times. The mRNA vaccines, I think, are definitely the way to go. They work better and they don't have some of the problems that you get with the other vaccines, which I'll get to on the next slide. They are essentially trying to mimic the things that your body will be making right now if you just ate lunch. So this is one of those particles that people tend to call either good cholesterol or bad cholesterol, depending on how they feel about it. It's really just cholesterol. And so it's a protein that wraps around a little ball of lipids and has got a core that's just full of little cholesterols. They actually make a little ball of lipids with a couple cholesterols in it, not so many, just a couple. And instead of putting the protein on the outside, because that would be a very expensive component to put in there, they use a lipid that has a little bit of polyethylene glycol on there, and it still wraps around just like the protein did. And then on the inside, you have a couple of these little orange squiggles. Those are the messenger RNA. And messenger RNA is like one of those James Bond messages that is destroyed right after you read it. It's in there. Half of it is gone within 18 hours and all of it is gone within a week. There's not a trace of it left. So all that stuff that people are worrying about, like long-term effects, it's not there and it doesn't leave any signature that could do those things. That's all complete nonsense. Last thing, if you know anybody who is vaccine hesitant, there's still time to actually get a vaccine before Christmas and get some effect from it. The vaccines take 2 weeks to work, and here's how we know. So the purple people got a placebo and the orange people got the vaccine. And those two lines both go up at about the same rate for 2 weeks, at which point the people who got the vaccine stop getting infected and the people who did not get the vaccine continue to get infected at the same rate as before. So you will get some degree of protection in 2 weeks. There's no protection really before that. But whether it's a booster or even a first-time vaccine, there is still, you still get a pretty good benefit for your buck and for your no buck, because you don't even have to pay for it. Yeah. So I don't know. I did. Yeah. 2 vaccines and boosted. There we go. Fine. How are we doing on time, Dr. N?
We were about a half hour in, so it's
Fine.
up to you. That's the beauty of Zoom, baby. You can go as long as
We're
you
almost done then. Yeah, good. Should you get a booster is the title of this slide. The answer is, yeah, you should get a booster. Yeah. So each of these little lines is a different age group. And just looking at them, you can't even really spot which ones are the old people and which ones are the young people, because they're all the same line. This is vaccine effectiveness over time. And so 1 month after your second dose of a 2-dose vaccine, you've got 90% protection, which is as high as you're ever going to get. And then it falls off gradually over time, such that over 5 months after your second dose, you are only about 50% protected from infection. And of course, if you get infected, this can spread to the kids, this can spread to anybody who's unvaccinated and do bad things. The protection against hospitalization holds up. But the nice thing is that a booster bumps all of these things up, way up. It increases your antibody levels higher than they were after, like right after your second dose. You'll get somewhere between 5 and 20 times as much antibody. And then you're just starting up higher. And so it's like sledding down a longer hill. You got just a longer ride because you started out higher. You put in the effort to walk up the hill. Good job. Yeah. All right. Here's why multiple doses of Johnson & Johnson probably won't work. So Johnson & Johnson's a different kind of vaccine. It comes in a little shell, and the shell is taken from a thing called an adenovirus. The shell is just a delivery truck. You want to get this thing inside, which is the spike gene, into your cells. And the problem is, over time, your cells will react not just to the thing inside that you want them to react to, but against the carrier, against the little truck as well. And if you make antibodies against this, you will shut down the vaccine before it has a chance to deliver itself. So the first dose works really well. The second dose works pretty well with J&J, and you get diminishing returns after that. You're unlikely to get much benefit out of a third dose. So eventually, probably we're looking at everybody switching over to either of the mRNA vaccines, and they don't have this. There's no protein on those that you can make a response to. So there shouldn't be any of this effect. Yeah. Jump past that. All right, ivermectin, because why not? So people take ivermectin on, oh my gosh, yeah, YouTube has a whole bunch of advice. Yeah, all the wonderful things it can do. Yeah, fine. I mean, there's YouTube videos on all the wonderful things that pyramid schemes can do as well, I would say. What it's supposed to do is it's supposed to block ion channels. So ion channels are these little tubes, little pipes in your cell that let like a potassium or a sodium or a chloride go in or out. These are how we think, among other things. These are what makes the little charge go down your neuron. The reason why ivermectin works and is pretty good is because it beats the heck out of parasite ion channels and does nothing to human ion channels. Now, COVID-19, SARS-CoV-2, doesn't have any ion channels. And the drug was selected because it doesn't do anything to the human ion channels. And that's really the only thing it can do. So yeah, we're taking a drug for a thing it can't possibly do. And honestly, that's a little weird, but yeah, if it makes people happy, I guess. But it's not doing anything. That's kind of the point. Yeah. And the last one, I got asked, oh my gosh, on the radio 2 days ago, but do masks really work? Oh, yeah. Here's the study. It's from April 2020, and the preprint actually came out in February 2020. And so they took people who were sick with actual coronavirus, the old kind, like regular human mild coronavirus. And so they checked how much they have in their nose, how much they have in their throat, and then they had them speak into a little plastic box. And then they filtered out all the big droplets and all the little droplets. So the big ones are called droplets, little ones are aerosols. And they had them do this first with no mask on. And so they got this much virus out. And they had them do it with a mask on and they got no virus out. Did it for the aerosols. And again, a lot of virus without the mask, no virus with the mask. Tried it for flu, pretty much the same thing, although there's a little bit that got through in the aerosol fraction on the flu virus. So masks are super effective against coronavirus, pretty effective against flu virus, but they're slightly worse. Yeah. Yeah. So yeah, it's the right tool for the job. All right, that's it. That's all I got. If you have questions, happy to do my best with them, and hope your holiday is better after this. Yeah.
Thank you, Dr. Newman. I'll give you the standard little applause on Zoom. Well done. Well done. We do have a few questions in the chat. One you already, I think, addressed, which was on the myocarditis, what it was called. You're welcome to talk more about it if you like. Then we have one, could we equate molnupiravir to essentially like a decoy then for the virus?
Yeah, little tiny decoy. Yeah, and viruses are dumb. They're fast and dumb, and we're taking advantage of that. Your cells are slow and careful, and they do not, they see molnupiravir and they say, no.
Right.
Yeah.
Dr. Els had a question. What do we tell unvaccinated COVID recovered folks who think their antibodies, I guess natural antibodies from having had it, give them comparable protection to vaccines?
A dose of COVID is about the same as a dose of vaccine. And we're probably looking at a situation where you need 4 doses to get something like full protection. I don't think anybody would recommend catching COVID 4 times because it's bad each time, most of the time.
I remember.
There's like a safe way that doesn't kill you. And there's this, I don't know. You know, there are still people that drive motorcycles without helmets and stuff. Just make sure you have that conversation at some distance because their antibodies are probably not holding up. Yeah.
Right. So I feel like I'm doing well having had COVID and three shots. So I guess
you may be the only fully vaccinated person in America. Yeah.
Right. Anyway, we can talk about that afterwards.
Fine.
If you do have questions, folks, feel free to drop them in the chat. You know, I'm happy to ask a few others. You mentioned that there were other areas on the genome that we could target with vaccines, and are there vaccines kind of in planning or production now to go beyond the protein spike? Do we know where that is?
We're planning one in peanuts. Yeah, we've got the nuclear protein. Can you imagine going into the doctor and getting a nice little packet of dry roasted peanuts? Yeah, with all your COVID booster needs met right there. Much better than a needle. Yeah. Yeah, there are people that are trying this, but right now the spike vaccines hit a little harder. And I think we need those as the first wave. And then I think for boosters, I think you have more options and maybe you want to diversify a little with some of these other things. Yeah.
Cool. And yes, to answer your question, Dr. Els, I will be posting this on the YouTube channel for the honors program, which I guess I could probably put the link to right now. That would make sense, wouldn't it? Like I'm a professional in what I'm doing. That's the link to the YouTube channel. So it will appear probably today. So basically, do you envision that there will be a need for boosters kind of, you know, moving forward for most everybody, at least for a year or two or beyond?
That's what we don't know, but based on the numbers that we've got right now, it still looks like this vaccine is holding up as well as the polio vaccine, similar numbers from each dose. And polio is a 4-dose vaccine. So that's why I'm saying it looks like 4, but we got to get to 4 and then prove that it holds up, and then we'll know for sure. But yeah.
That's great. That's edifying.
Yeah.
So Kevin asks, so you're working on oral ingested vaccines then? That's kind of somewhere we're going.
Yeah.
Cool. Very
Why
cool.
not try it, right? Yeah. Might get to some people that otherwise would be hard to get to. And you don't need to refrigerate peanuts at minus 80 degrees. Yeah, that's the nice thing. Yeah.
That's useful. Might be fun if you did, I guess. All right, Dr. Morton asks, first off, he says, thank you, Ben, for all of your hard work on this. Are you modifying your behaviors this holiday season? He says, I'm assuming you're boosted and wear a mask when you're out and about, but are you taking any additional steps?
I've been pretty much a hermit since the start of COVID. Yeah, I don't know. Maybe it's my nature. I don't know that that's much of a modification. We're planning to visit my parents, and yeah, that part will be vaccinated but unmasked, and everybody there is. But I'm still doing it. I'm clawing the table a little bit, even as I say that, because it makes me nervous. I'm going to try to be very brave and do it, though. Yeah. But yeah, I wish other people would also modify a bit. Yeah, that would make things better. 4 straight weeks of rising cases in the US, and that worries me.
Yeah, no, absolutely. Dr. Chan asks, will Omicron be more aggressive than Delta?
Signs right now are that it's not, but it's more like an absence of data. You can only get, so how does this even work? Like this competition. The idea is you take a person who's out doing something really dumb, like no mask at all, going to, I don't know, giant bar concert, something like that, whatever. Yeah. Travis Scott concert, something like that. So in that situation, they're going to be exposed to a number of people who are positive. And the virus that gets them is going to be the one that comes out in the greatest numbers, that's being exhaled more than the others. And so far in those competitive situations, it seems to be Delta. Now, we've got a little spread of Omicron, but it's just from people who are like in the same family as somebody with Omicron. And so we don't know for sure that it's going to be able to compete. And frankly, Delta has driven everything else to extinction. So I'm optimistic that Delta will crush this contender as it has with all others. And the vaccine works great against Delta. So that would be weirdly, yeah, weird to find me rooting for Delta. That's very weird, but that is where we are. Yeah.
As a Giants fan, it's how I feel watching the Cowboys and Eagles play. I guess I'll cheer for Delta then.
Sure. Yeah.
Anyway, are there any other questions or anything? Oh, here we go. Do you have any information on fertility issues in COVID vaccines? I've frequently heard people commenting on it, but I don't think it holds water, Caitlin says.
There was one dude who said that there's a little part of the spike and it does a similar job. It doesn't actually look similar, but it does a similar job to protein that is involved in basically feeding the baby in the placenta. It's called syncytin. There we go. And based on that, he said, do we know if anything might be happening? And then we had hundreds of thousands of people in the US who were vaccinated while pregnant or gave birth while vaccinated, while pregnant, stuff like that. And no increased rate of complications of any type, no infertility. So it turned out to be nothing, but this, yeah, I don't want to call him a jackass, but yeah, is the entire reason why we're having this discussion right now. And frankly, I wish he'd just zip it. Yeah.
Right. All right. So about the difference between infectability and severity of a resulting disease, is Omicron more likely to successfully attach than Delta and or be worse if and when it does?
Nice. Yeah. Good question. There was a paper last week that looked at different risk factors, like looking at all your tests that you would get if you go to the hospital with COVID. So they'll measure all these things in your blood and they'll measure the amount of virus. They compared them all, and the only one that was actually predictive of whether you're going to stay in the hospital for a long time or get much worse was the amount of virus in your body. And so Delta makes about 4 times as much virus, per pound as Alpha did, which made more, like 1.5 times more than the old variants did. Omicron, we do not know the number for this yet. It has a couple of mutations that look like it would make it a little faster and a couple of mutations that look like they would be crippling. And all the mutations that we see on Omicron have popped up in other variants that Delta has crushed into extinction because Delta was faster. So that's why I'm optimistic. Once again, that go Delta, go Cowboys, go whatever. Yeah.
I don't know which one's which in this case.
Right. Or yeah, Eagles. I don't even know. Yeah.
I don't like either of them. Do you have any information on the rates of long COVID or autoimmune disorders arising from COVID infection, and is it different among variants?
Yeah, I have not. It would take a very big study to do that. And the problem is that long COVID happens, but it means different things. Some people say long COVID is when you have the virus, and there are people that hold on to the virus for 200 days. And so that is long, literal COVID, whether or not they have symptoms. There are other people that say long COVID is all these kind of health after effects after the virus is gone from your body. And so there isn't a study that I can point to that is definitive on that. And because all these things are kind of rare, you would have to be dealing with a cohort of, like a couple 100,000 patients to get enough long COVID patients to make it worthwhile. And I think Israel could probably do that, but I'm not sure anybody else could. And we keep raking over that Israeli data over and over again. It's great data, but yeah, I'd like to see another data point for sure.
Okay. We probably have time for another question if anyone has one. I'll give it a few seconds to magically appear in the chat. It's very exciting. There it is. I will say, hopefully next year, when you return for your contractually obligated December virus lecture for the rest of your natural life, maybe we can talk about a different virus. Who knows? Maybe the world will be in a place that we can not talk about. I'm not optimistic. I suspect it'll be COVID variants part 7 by then, but who knows? Maybe.
Well, you saw South Park just did the 20-year time skip and we're still dealing with COVID. So I don't know. Yeah.
Okay, I don't see any more questions. I do see thanks, Ben, from Dr. Chen. And I would say, yeah, thank you very much, man. Very much appreciate it. I'll give you another little applause from Zoom.
Okay.
It was great to see you again, albeit virtually.
Likewise. Yeah.
And I'll go ahead and get this posted once we're finished. And thank you everybody for coming. It was great.